Okay. Um, I've heard that there are more homework questions. Okay.
Okay, so looking at page 14 of your notes, and
Notes I don't have with me. Yeah.
yeah, you're welcome. Here, do you want me to like?
I can pull them up on here.
Okay. I mean, it's you can probably answer without it.
Okay.
But what I'm getting from this is, when we're finding the coefficients, when we're doing our stencil and everything, and we find our A's, essentially, like here it's like center difference. So our center difference approximation is essentially just like adding those coefficients, just saying like A1 plus A2.
Oh,
does that make sense?
wait, A1 plus adding the coefficients themselves?
I mean...
Okay, which stencil are you talking about? Okay.
I guess I'm trying to like...
You're multiplying the coefficients by the values of U.
Yes.
And then you're adding them.
Yes.
Okay.
Or I guess maybe more a lot, because I'm looking at problem 2B, and I don't want to multiply out that system of equations. You know what I'm talking about?
Oh, from a four folders stencil?
Yeah.
Okay.
So what I think that I can do is essentially write a program. I can use whatever H I want.
Yeah.
And for those H, or for that value of H, I have coefficients. And those coefficients kind of relate to that like D matrix. Yeah. Kind of like that. Do you understand kind of what I'm talking about?
Not really.
Can I just draw on the board?
Yes.
Okay. Maybe.
I feel like we're speaking different languages.
So, thank you. Okay. So here's that matrix with whatever. Here's our A's equals, I think for this problem it's like, okay. So once we get those A's, let me think. Doesn't it, usually we're solving like D squared, which this is like our center difference, right? Matrix.
Yeah.
And so here we'd essentially just be using like the A's as entries of that matrix.
Yes, we
so
are.
It's usually like 1, -2, -2, whatever. But
way around, but
whatever. You know what I mean? But like essentially it's like A0, and this is like A1, and this is A1, and then like A2 or something.
As long as you figure out how you index, yes, you can.
Okay. How do I know the order?
Okay.
Because I have through A0 through A4, and I don't know.
Okay. All right, now your question is this. So that's your question.
Yes, that's my question.
Okay. Because within this system, it doesn't really matter how you order. It doesn't matter until you get to here.
Yeah.
So what has to happen is on the main diagonal,
that's going to be A0.
Has to be, or in other words, whatever corresponds to x0 bar, which way we define x to the bars is always 0. It corresponds to our, so it's based on the convention we've been using in the examples, it's A0. Mm-hmm. So, okay. So then in general, diagonal number D, where using like MATLAB's convention of the main diagonal is diagonal 0, the super diagonal is diagonal 1, the subdiagonal is diagonal -1. and so on, using that convention, diagonal number D corresponds to point x0 plus D times H. So, for instance, for a fourth order stencil, using 5 points, you're using x naught and then x naught plus or minus H, and then plus or minus 2H.
Yeah.
So, however you choose to assign indices like A0, A1, A2, A3, A4, that's not what matters. What matters is which points do these unknowns correspond to. So, which of those corresponds to a point x naught plus H?
Isn't that A1?
That,
Your super diagonal?
Yeah, yes, it's your super diagonal.
Yeah.
I've been using it as A1 in my examples, but my examples have only used like x naught plus H, x naught minus H.
Yeah.
So if you want to continue that convention, but then I've been using A2 for x naught minus H,
yeah.
So that is what should go here.
And then would A3 kind of go, well, beside A1?
If you've assigned that to x naught plus 2H, then yes.
Okay.
So if you'd like, we can just agree on that's how we're going to number these unknowns.
Yes.
Okay. But I'll just write that explicitly so everybody's on the same page. It's x naught plus H, x naught minus H, x naught plus 2H, x naught minus 2H. Okay. And then, all right, so which weight you're talking about stencil, which point, and then which diagonal, but that comes directly from the multiple of H.
Cool.
I want to mention a function I have online that might be. Okay, so trying to find this function, because I know I've posted before for different classes. Under numerical differentiation. Ah, yes. Okay.
So, for instance, if you go to my site for 772, on the lectures page, and the entry for September 14th, when I covered numerical differentiation, there's a function I put there, diffrule.m.
And what that function does is, let me open up real quick. Okay. So if you give it
a list of indices, but actually, really, it's these multiples of H. So that's a way of telling it which points you want it to use. For instance, you might give it the points -2, -1, 0, 1, 2 for this case. And then the second parameter, so you give it a, it's unlike most of my code, this is actually documented. So first parameter is a vector of multiples of H that you want to use. That tells it which points, x naught plus IH. And then the second argument is, what order of derivative do you want? So in this case, it would be 2. It'll give you the coefficients. It basically solves this system. You just have, basically for H equals 1. And then you just have to divide by, in this case, H squared for your differentiation rule. So you don't have to go to the trouble of actually solving a system. What
But
this,
if we just, because we're going to have to use some value of h anyway anytime that we run the code.
yeah,
so we can just set h and solve with that given h, right?
you could, yeah.
Okay.
Yeah, you can have your code do the work. Yeah, because what this function does is it forms the Lagrange polynomials for those points, and then computes a derivative of a Lagrange polynomial and evaluates them at basically at 0, and gets through all that way. So it's a very different approach, but equivalent to this. So we go away and check if you're doing something else. Okay. But yeah. So whereas it doesn't really matter how you order things in the system, here it's and now the reason why this ordering is important is because this matrix is multiplied by your vector of unknowns, which are all in order. So based on the grid. So it just says these go from left to right. In terms of x, these entries also have to follow that order from left to right. Okay. More questions?
Possibly. Hold on. Give me 2 seconds.
Okay, well, anyone else is welcome to chime in too.
So on part C,
Okay.
We're supposed to be getting what fourth order conversions?
Right.
Okay. So what if I'm getting greater, like what looks like greater than fourth order conversions? Like I did something wrong.
Oh, okay. I wouldn't rule out greater than fourth. Although, actually, when we looked at that code from MIT, it seemed to deliver exactly fourth.
Yeah.
So, what's that based on? Like based on the slope or something? Or
Yeah. I was just looking at that slope between 2 points.
okay.
And it was, because it should be if I'm halving things, right? It should be, well, I think I was just looking at like, because the slope should be like 4 or something.
No. Okay, so like for your business, you're cutting h by a factor of 2.
Yeah.
Okay, for fourth order accuracy, if you cut h by a factor of 2, then the error should be decreased by an error of 16. 2 to the 4th.
Okay. Yeah. Well, I'm gonna have 27. So I messed up.
It depends on the because that order of accuracy really applies most rigorously as h gets closer and closer to 0. You may see different trends for larger h. Now, are you trying this for like a lot of h's, or?
I tried it for 3 different values.
Okay. Now, have you done like a plot of them?
Yes, I have in mind.
Okay.
So this is from part C only.
Okay. Also, the slope differs. Okay.
But my slope differs in part A. If you look at the other one, there's another thing in that screen that has part A versus part C.
All right. So.
Yeah.
So we have 2.5. Oh. Can you show me your plot command?
Yep. Where is it? So H is errors. It has C afterwards. If it's from part C, it has A afterwards if it's from part A. And I just ran the program and then saved what it gave me as the errors.
You're supposed to do a log.
Oh, okay. Cool. I can do that.
Which makes it surprising if you got a straight line anyway.
Okay. Okay, so yeah, error versus H should be a log plot. Plug. Yeah. With a slope equal to whatever order accuracy you're expecting. Okay.
Okay, it looks exactly the same.
What?
The two different ones look exactly the same. It looks exactly like the same way that it did before. Yeah. No, the two different ones look different, but it might be.
Okay.
Okay, well, I'm going to ask something.
Okay.
And I'm sure that you've already talked about this, but I'm going to go ahead and ask again.
Okay.
So, in 2A, and I walked in class a little bit late, but I have notes from what you're talking about. But,
Yeah.
So he asked us to use the Taylor expansion to explain the observed error convergence rate.
Yeah.
So, but the notes I have on that are like code stuff. So you want us to use the Taylor expansion?
Okay, there's two parts to this.
Okay.
Because
I know you've already talked about this.
that's okay. Because with maybe of course. Okay, I'll just do a disclaimer here, but I copied it straight off the MIT side with just minimal modifications, and if I'd written something myself, I'd probably explain it a little more clearly than this. Because in the part before part A, which is write a program to approximate this, blah blah. Even though it doesn't explicitly say that, but it's kind of implied by what's in part A. Once you have your program that will compute the solution, and plus the fact that you're able to get an exact solution, then you need to compute the error. So that's like your, and then you can use that to get what is referred to in part A as the observed convergence rate.
Okay, so you compute the error from this program of solving this linear system.
Right.
And then you compare it.
Compared to the exact.
Okay, compared to the exact.
Yeah. Using whatever norm of your choosing.
Okay.
And then you check, like, okay, is the error going to zero? Like as you decrease h, is the error going to zero at the rate of h squared? Is it quadratic? And then use a Taylor expansion to show that theoretically you're also supposed to get second order. Okay.
So I have a problem with analytical section of it.
Right.
I know how to start. I have the Taylor expansion, but I've seen a section, page 25 of your notes, that it shows after Taylor expansion, we got this.
Okay.
But I don't know how to substitute this one to get the second line here.
Okay. Is this also part A or?
Yes.
Okay.
Fine.
Okay. Okay. So what you would do is you would use that expansion. So what she has in her paper is this Taylor's theorem, generic Taylor expansion, with x equal to x naught plus h and x naught minus h. So if you look at the PDE of this problem is that minus uxx is equal to f. So then you have minus u of x naught plus h minus 2u of x naught plus u of x naught minus h all over h squared.
minus equals f at x naught plus local truncation error. So, like for instance, without getting into Taylor's theorem much, you know that the first term in any Taylor expansion, so you use Taylor expansion on these. Around x naught. Well, the first term in that any Taylor expansion around x naught is going to be u of x naught. So you know that all the u of x naught terms are going to cancel. So then you're not going to have like a 1 over h squared term in there, thankfully, because that would be very bad. But then when you keep going, I would recommend at least going out to the fourth derivative, and canceling whatever you can, and you use the fact that u double prime or minus u double prime is equal to f. Okay. Anything more?
Can we like work on it and then like ask you questions as they come up?
Yes. Yeah, I mean, we could kind of turn this into a office hour of sorts, but
Oh, that would be really cool.
yeah. But so no one else has questions at this time?
I certainly will, but I'm not going to ask them.
Okay. Yeah.
On my computer, can you look at the code?
Okay.
Okay, right here. So we're not
Yeah. Oh, right. That punch behaves a little differently, I believe. Yeah, I think I was going to include boundary points. Yeah. Well, I mean, you could, because those might come in handy for other things, like plotting solutions. As long as for your right-hand side, okay, I'll go front so I can be heard on the recording. Okay, so yeah, MATLAB has a function lin space where you give it an A and a B and a number of points, and it'll give you a vector of that many points from A to B, including A and B. So for the purpose of making your right-hand side, like when you plug into your F, you want to not include, actually the easiest way to do this, so if, so if you take lin space 0, 1, n, let's say, where n is the number of points you want to include. So then to get the interior, you can take x2 colon n minus 1, and that'll give you a vector of the interior points only. As Haley and I discovered yesterday, that when you're building your right-hand side, or also like your exact solution to compare against, that if you're off by 1 in terms of your indexing, as far as what points you plug in, it throws things off in a very interesting way. So and because since you know how to get the exact solution in this case, if you go ahead and plot that, and you also plot your computer solution, generally they should be dead on. I would recommend using at least like 100 points or so, just so your plot will produce a smooth curve. Let's see if I have anything else preemptive. Well, anyone else is welcome to chime in at any time.
About part D, number 2. Yes.
Yeah.
Well, this is my problem. I don't know how to make these boundaries.
The boundaries?
These, yes, I mean, isn't it boundary x less than half?
Oh, you mean like to make the right hand side?
Yes.
Or, well, what you can do is you can make a. Oh, well, okay. So in this case, since you want it to be 1, only for x is less or equal to 1
It should
half.
be inside a for loop to make that.
You could do that. Actually, I'll show, okay. I'll show you how you can use MATLAB's indexing to do it particularly efficiently. Because let's suppose that you already have x. Well, okay. I'm going to assume that x is a vector. Okay. So we have a vector of interior grid points, like they did that 2 to n minus 1 earlier from a result of Lin space. Then you can do this. If you define f to be a 0 vector of whatever length you want, so we're assuming n by n matrix, n interior points. Okay. So you start out being 0, but then you want to take the part for which x is less than or equal to 1 half and set those elements equal to 1. So you can say f, and then x less than or equal to 1 half is equal to 1. So what this will do is this is MATLAB's logical indexing. It will figure out the indices of x for which the values are less or equal to 1 half and set f at those indices equal to 1.
Oh, I didn't know that I can use these kinds of. Okay.
Yeah. Yeah, well, that's why I'm pointing out, because I'm sure that other people here didn't
It's
even.
much easier.
Yeah. Yeah, because the alternative would be like a for loop over like for I equal 1 to n, and say if xi is less than or equal to 1 half, set f of that element equal to 1. You can do that too, but yeah. I want to give it something that's equivalent here, just because I want to make sure you guys are aware of this function in case you want to use it for anything else. If I set a variable indices equal to find, and then you can put any condition in here, like this one, and then you can say f ins is equal to 1. So this does the same thing as this. In fact, this will be a little faster. But I want to make you guys aware of the find function because there are many situations where it can be useful to extract a portion of a vector or even matrix where some condition is true, and then do something with that. There's something else I want to look into from this same part, problem 2D. Okay, so we have a situation minus uxx is equal to f, but f in this case is equal to this piecewise constant function. Okay. So, as far as constructing an exact solution, because as far as the boundary conditions are concerned, we have u of 0 and u of 1 are equal to 0. Those are the only conditions that we have. So, okay. So if I were to integrate f, so the integral of f, an indefinite integral, would be equal to x plus c1, and then just c2, which is an arbitrary constant. Okay, and I'll call that big F. Then I integrate again. So u would be minus the integral of big F. Because it's minus u of x is equal to f. So then I have minus x squared over 2 minus c1 x minus c3. And then I have minus c2x plus, I can actually do plus here. Okay. I don't like to have so many minuses, so I'll put minuses here. Therefore, all my arbitrary constant terms will be plus. But they're arbitrary constants anyway, so who cares? Okay. The point is, it has that form. But I have 4 arbitrary constants, and I only have 2 conditions to impose on them. So, for example, if I want the u of 0 to be equal to 0, I plug in 0 here. That tells me that C3 has to be 0. So that's nice. That term is gone. And then I have u of 1 is equal to C2 plus C4. So that also has to be 0. So that means that C4 is actually equal to minus C2. So now I'm down to 2 conditions. And, okay. Can anyone suggest what additional criteria I ought to impose? So 2, because I have 2 arbitrary constants left, to determine a unique solution. Yeah, because I had 4 constants. The boundary conditions help me eliminate 2 of them. I have C1 and C2 left. So whatever condition could I make the solution satisfy? I've run out of boundary conditions. It satisfies the PDE. Okay. Continuity. Because the second derivative, as we see here, is discontinuous. But at least we can make the function u and its first derivative be continuous. So at x is equal to 1/2, so u and ux at 1/2. So if I plug in 1/2, I have minus 1/8 plus C1 over 2 must be equal to C2 over 2. And then for the derivative, I'm going to have, okay, so minus x plus C1. Okay, so this is for u, and then for ux, I have, okay, so minus x, so minus a half plus C1 must be equal to C2. Okay, so actually, if I multiply the first equation by 2, oh, not liking that at all. That's not going to have a solution. It's a inconsistent system. Okay, so oh, wait a minute. For u, I messed up. It's C2 over 2. I'll put these back. I forgot this term. So C2 over 2 minus C2, that gives me minus C2 over 2. And now I can multiply both sides by this equation by 2. Okay, now we're good. So, put another way, C1 minus C2 must be equal to a half from the second equation, and C1 plus C2 must be equal to 1/4. So then you can solve that system by elimination and construct the exact solution to compare against. Okay, those are values of C1 and C2. Okay. Oh, that was fun. Yes.
I'm having a problem.
Okay.
So it's 2b, and I figured out, like, from the notes that you were talking about yesterday with the coefficient, this is still kind of the part that's on.
Yeah.
It's, you were saying to take, like, something about the boundary into consideration, right? So looking at, like, x0 plus h, then x0 plus 2h, and then 3h and 4h.
To modify stencil. Yeah.
So instead of this kind of thing, what I'm gonna have in this problem is like A0, A1, A2, A3, A4.
Right.
Right?
Yep.
Okay. Okay. So I don't know why it's not working. Because that's what I have. Like this is A0.
Because now you're pulling a stencil to the entire system.
Well, that's what I have. Like, here's for that stencil. Here's the matrix, and then I have this is my S, this is my D, and then I just solved for my
Right.
A.
Well, yeah, but the thing is, you're only supposed to use that stencil in the first row. So, do you already have a center difference rule for fourth order? Oh, you're using this stencil throughout.
Yeah.
But that won't work at the outer boundary.
Okay.
That's the problem. So what I suggest is make a centered stencil. Go ahead and make your matrix based on that first. And that will work for every row except the first and the last. Do this stencil for first row, and then do the corresponding stencil where you replace H with minus H and go backwards at X naught minus H, minus 2H, etc.
Okay.
For the last row.
Okay, so that's only on the boundaries.
Right.
Okay. Sorry, I'm thinking.
Okay. Okay. Yeah, because you could use that stencil for every single row until the very last row that uses two boundary values and assumes that the boundary value is 0, which is correct, and then the value past it is actually for that stencil it'd be 4 points off the boundary and 3 points past. It'll assume they're all 0, which they're not. Oh, your son. Okay, so it's calling your. Oh. Oh, yeah, I see. Yep.
And when I do this, when I use the backslash, if I'm doing D backslash F, since I did my F with the X, do I need to do F of X?
From the right hand side, as a function handle, is you call f of x to get your right hand side, and then that'll give you a vector, and you use backslash on that vector.
Okay, so on the F of X, not just F.
Right. Yep. Okay. Does anyone have any questions at this time?
I'm having a problem with the error.
Okay. Which problem?
When I
Which part of 2?
A,
Okay.
when I get the error the first time, then I'm supposed to change my H, right?
Right.
When I change the H, am I dividing it by, how am I changing the H?
Well, it's like, for instance, if you reduce h by a factor of 2, for instance.
Right. So if I divide it by 2, when I compute the error after I change it, it's not
Decreasing.
I'm not changing anything but the H, right?
H and N have changed together. So really, I guess, okay, maybe instead of, just go ahead and increase N, which would have the effect of reducing H.
So I divide by 2.
Or we just get multiplied by 2. Okay. So one last thing to add based on the question I just got. So I had to correct something that I said yesterday. So matrix D2 is second derivative matrix, standard tridiagonal approximation. Okay. Then D squared is vector F. If F is a vector consisting of the values of your function at the interior points, that is equal to second derivative at your x values. Again, with both of these, can't emphasize enough, interior points plus second order error only if f is 0 on the boundaries. So here's how you fix that for a case like this. If given f in a problem where it is not 0 on the boundaries, that whatever boundary terms would be produced by using this same stencil at every single interior point, you just have to move that to the other side. So actually, I'll just write out what the terms are. So the correction is d squared f plus 1 over h squared times a vector that is all zeros except first element we have f of x, f of 0, and then down below f of 1, and then zeros in between, and that should equal f double prime at your interior points plus order h squared error. So just accounting for those, yeah, since a given f does not satisfy boundary conditions, I forgot about that yesterday. So, yeah.
So if you did the first problem where the boundary conditions are 0, so there are no boundary,
Right.
nothing to add,
Yeah.
and then you wanted to use that same code to do the problem where there is boundary conditions, you could just do this instead of going and modifying the right-hand
yeah.
side.
Well, in fact, this is kind of sort of how you handle a case where we have non-homogeneous Dirichlet boundary conditions that need to do a correction like this. And then the only reason this came up is because we're trying to use f double prime to get the fourth order accuracy. And at least you can do exactly this, in MATLAB to get those boundary values like I just had you do there.
So literally, like where we're updating f, like we make f like we did in problem 2, and then we were just adding on that like d to f. We need to also add on 1
This
over
vector.
h squared times that column vector.
Yes.
Okay.
Or just fix those first and last elements.
So we don't have to do anything.
Yeah. So essentially, what I'm doing is
Yeah.
I'm just gonna make a vector.
You see, you go first to H is 1. Then after you solve the
And then
dimensions,
like, yeah, your
there would be
dimensions.
H in there.
Right.
And
Yeah.
then you do a few values so that you can see as H reduces
Yeah.
what the error is.
Yeah.
So what would be the starting H? Is it determined by the stencil spacing?
Really, best in terms of the number of grid points, as h comes directly from that. I would say for this particular problem, I'd try like n number of grid points being like 100 or so.
Actually, yeah.
Because then at least you should get a reasonably accurate solution.
So h is 1 over the number of points plus 1.
Right.
Okay. And so that has nothing to do with the stencil points.
No, I mean, for stencil, yeah, I only suggest setting h equal 1 just to see what the coefficients are.
Right.
And then whatever coefficients you get, then you in your stencil, you divide by h squared.